I also noticed today that there are 3 microphones up here, which is pretty intense. Any questions about anything? It doesn't have to be about assignments 1 or 2. Okay, I'm picking up a signal actually. I just picked up a signal. Somebody just was thinking, did you start assessing coursework 1 yet? And the answer is no. Who was thinking that? Somebody in this room was that flashed through their minds. I felt it. I heard the signal. This is the attendance, my personal register. Any questions about assignment 2? Anybody started yet? Well, hopefully you at least started to read it. Hey, look. Poor you now that I know your name. Poor you now that I know your name. Okay, so we were talking about the marching cubes algorithm, which is a little bit difficult, some of the steps to understand. Anyone have questions about this? Any steps so far? Good. And so last week at this time we went over the marching squares, and probably everybody that's here now was here then. And then today we started to go over the 3-dimensional version of marching squares, marching cubes. So start with a cell, define your cell, classify every data value at the vertices as above the ISO value or below the ISO value. Then for every intersection or every above and below value, create an index. 1's for inside the isosurface and 0 is for outside in this case. There are only 256 possible different indices or possible different combinations or possible different classifications of the vertices. It's a very finite number. Therefore, you can predict the corresponding edges for all 256 cases. You can compute them or predict them and use that to store a lookup table. So the lookup table does a lot of the work. It's pre-computed. It's this pre-computed mapping between index and triangle edges lists. And there are only 15 unique ways that the surface can intersect a cube. Right? There are 256 different ways, but there are only 15 unique ways because of rotational symmetry and reflection symmetry. And this is just one example of taking as input the index that we computed in the previous step or in this step, and then returning as output the triangles. So the input is the index on the left-hand side of the table. If you want to literally imagine a table with 2 columns, the left column is the index from 0 to 256 in binary, and then the right column is the list of edges that correspond to those indices pre-computed in a lookup table. So the input is the index, and then the output is the set of edges. And it's always three sets of edges, because three edges or three edge intersections form a triangle. And surfaces can be or are often composed of triangles. And then once we've got the edge intersections, we interpolate the edge intersections between the data samples of the cube to make them more accurate, to make the surface more accurate. After we've updated those positions, we interpolate, or we compute the gradients at the cube vertices and then interpolate to update the triangle normals, the triangle vertex normals. That's not the only way to compute triangle normals, normal vectors. Anybody remember what triangle normals are used for? Little trivia question. Well, I guess it's not just trivia, but a little academic question. Anybody remember? Somebody did mention it this morning. Ziggy.
For like lighting, like ray tracing and shadows and things like that. So
Lighting and shading. Nice, Ziggy. You're a smart guy. You know that? You're a smart guy, I can tell. Correct, lighting and shading. So that's the computer graphics part. Lighting and shading is a computer graphics part, so to speak. The last step of the viz pipeline. So what is there's a gotcha in the algorithm, like a snag, if you will. And those are ambiguous cases. So you can imagine ambiguous cases 3, 6, 7, 10, 12, and 13 in this slide. But here's what one of them looks like in 2D, in 2 dimensions. And I think somebody was thinking about that earlier today. They were thinking about these ambiguous cases. So look at these 2 squares. They're actually exactly the same if you look at just the 4 data samples. These 8 data samples are exactly the same. So there's 4 here and 4 here, and they're the same. But the way they're interpreted, one is interpreted as 2 isocontours passing through this way, and one is interpreted as 2 isocontour values passing through this way. And they're both actually valid interpretations. They're ambiguous. Because remember, all we're doing is looking for at the edge intersections. The algorithm is always looking along the edges of those cubes and those squares. It's always testing these edges to see, okay, do I have a data value on opposite sides of the ISO value or not? If the answer is true, then there's an edge intersection. If the answer is false, there's no edge intersection. So here we've generated 4 edge intersections, 1, 2, 3, 4, and same here, 1, 2, 3, 4. They're the same 4 edge intersections. But it's just how they've been connected to form polygons that's changed. And here's another ambiguous case in 3D. That's the same. It's not exactly the same, but it's another ambiguous case. If you look closely, you'll notice that these 8 data vertices have the same classification here and here. And they have the same edge intersections, right? The same 6 edge intersections. But the way those edge intersections have been triangulated is different in both cases. Those are called ambiguous cases. Now, how do you resolve that ambiguity? That's an advanced test question, and that does appear on the test sometimes as a question. If anybody's interested, anybody happen to know already how you could resolve that ambiguity? Well, probably the simplest way is to subdivide the cube or the square and then run the algorithm again on the subdivided cube. So you could imagine subdividing this cube into 4 smaller cubes. You can interpolate the value here based on these 4 values and subdivide the cube into 4 smaller cubes and then perform the marching squares on those 4 squares in this 2D case. In the 3D case, you'd have to subdivide the cube into 8 smaller cubes. In 2D, it's 4, and in 3D, it's 8. And then run marching squares on those smaller. Or not even run marching cubes on the smaller ones, just test the sign of the center vertex to see if it falls above or below the ISO value. Imagine I subdivided this and derived the interpolated value here in the middle. Well, if it's on the same side of the isosurface as these two, then this is correct. If it's on the same side of the surface as, or the ISO value as these two, then this one is correct. And I could resolve the ambiguity that way. Same in 3D. Here's some more about that. Like, this is what happens if you don't resolve the ambiguity properly. There's a hole in the surface. And here's the correct triangulation, so there's no hole. So the left one is correct, the right one is ambiguous. And this is a false triangulation. This is the correct triangulation. Another method that's a little bit more sophisticated, a little bit more complicated, is we assume that the isosurface forms an asymptotic or a hyperbolic surface, right? We just assume that the isosurface passes through the cube these 2 ways. And then we test the intersection or the hyperbolic point here that the two surfaces form. We test the sign. If the sign is the same sign, by sign I mean inside the isosurface or consistent with these two, then it's on the same side, then this is correct. If the sign of this point is consistent with these two, it means we have the other configuration that's shown in the other slide. It means this assumption is incorrect. And the surface passes through it this way instead. It's a little bit more, it's very similar to the subdivision. Just the point that you test is a little bit different. And that is it, basically. So there are 256 ways the surface can pass through a cube. We know that already. And we reduce those 256 combinations to 15 unique ways that we have a few ambiguous cases that we need to handle. And ambiguous cases cause holes if arbitrary choices are made. And the maximum number of triangles that can be produced by a single cube is 5. Here are some examples of isosurfaces. Now these are multiple isosurfaces, by the way. Like there's a semi-transparent isosurface for the skin, soft tissue, and bone. And here again, skin, bone, soft tissue, more soft tissue. These are from vector field visualization. Those are different kinds of vector field isosurfaces. Here are more isosurfaces. Surfaces of constant valued scalar value. And this is the paper you read if you want to see all the details, more details. And you find a copy of that on Blackboard but Google Scholar can also provide you with a copy. It's not a big deal. Now, one of the advantages of the marching cubes algorithm is that we don't need to load all of the data into memory at once to generate an isosurface. So imagine you have a data set that is terabytes in size. You cannot just load a terabyte of data set into memory and then compute a surface and then like release the memory. It's just not possible. One of the great strengths of the marching cubes algorithm that makes it so popular, it is very popular, is because you only technically need one cube of data in memory at one time. In practice, it's not that way. In practice, you load in 2 slices of data, 2 slices from the volume, and you swap in and out slice by slice. So it's very good with memory management, very, very good. So we can process arbitrarily large data sets and generate very large isosurfaces. This is one of the reasons it's so popular. And there are other solutions, by the way, to the ambiguity problem. Those we just talked about too, but there are more. Any questions about the marching cubes algorithm? Good, good. If you do have any questions, let me know at any time. I might have some kind of surfaces. Do I have some surfaces? Yes. Some more examples of multiple surfaces, by the way. That's multiple surfaces. It's not just one. There's a semi-transparent surface for the skin, and the bench, or whatever you want to call it. I can't remember what you call that thing that you use to carry cadavers with. Stretcher, maybe? Something like that. There's another surface for the bones. And you can see the lighting and shading, by the way. And you can see it much better when you can rotate the image. So let's see, what about this one? I don't think this one is much different. It's very similar.